think we have already had some idea of what mathematical modeling is about and what are the skills and competencies that we want to our students to develop through mathematical modeling. And we have also talked about perhaps some of the principles in designing mathematical modeling tasks. And then at the last session, I gave you a challenge, I gave you some homework. I said go back and think about what activity you might design, right? And hopefully later on, the second part of today's session, we will share our resources a little bit, and then we'll see what we can come up with. But before we even move to that, let's say you already have the idea and you have an activity and you have some problem that you think that is suitable for your students as a mathematical modeling activity. How then do we translate that into a mathematical modeling lesson in the classroom, or even a project for your students? I think having the idea and designing, you know, the problem and so on is one thing, but really going down to the real pedagogy of it and delivering it in the classroom, sometimes we are not so experienced, right? So we need to be able to have some kind of guideline. So the framework that I'm going to introduce to you basically is a set of guidelines, some guiding principles that will help you translate whatever idea you have now, you know, in terms of designing or implementing a mathematical modeling activity, translate that into a real practical kind of thing in the classroom that you can carry out. Okay, I also mentioned last time that there are several different researchers who have come up with different kinds of diagrams, you know, for the modeling process. So before we dive into the framework itself, let us look at some of these possibilities. Huh? Okay, this one is from Gloria Stillman, Peter Galbraith, Jill Brown, etc. This is a group of researchers in this area from Australia. Okay, and they came up with this diagram. Don't have to take down everything. You know, this is it's not. You can Google it and you will find it somewhere on the web. So it's fine. But the main thing is that you notice that they start off with some kind of messy, they call it messy real world situation, and then they have a mathematical model somewhere and then have a mathematical solution. And the cycling, or the process where you go in a cycle, repeatedly and so on, is usually within here. Okay? This is another one. This is Bloom and Ferry, and this is a group of people from Germany. Okay, Werner Bloom is a German, and similarly, you see they start off with a real situation or problem, right? And then they have a mathematical model and the mathematical problem, and they have mathematical results or solution. Okay, so you see, this is where it goes round and round. Of course, it goes back, but this going back is to provide the solution to the real world problem. Okay, this is another one. This is also from Australia. It's the New South Wales Department of Education model for modeling process. So again, same thing. They start off with a real world problem, and then as you can see, formulate problem, and there's some cycling over here as well. And then they end up with a stage 7 where they have a report. So generally, that is the usual picture. This is the one that I presented to you. And you can see again, you know, we start off with a real problem, we want to go to a real solution, but then we go through the mathematical world in order to get a real solution. But in general, you see that we always begin with a real world problem, and we hope to achieve or arrive at a real world solution. Okay? We do that by casting the real world problem into a mathematical problem, and then hopefully after solving it, we are able to find the mathematical solution and then match it to our real world solution while interpreting it. So this kind of picture is so generally that should be the idea, right? Okay, so from the last few sessions, we have already agreed that in order for students to be able to learn mathematical modeling, there should be some meaningful modeling tasks for them to acquire certain skills and competencies. And then we say that this can be small scale kind of seed work, or it can be large-scale project work. And some of the tasks may be very specially designed just for some very specific skills or competencies, right? And we also went through the whole process of distinguishing between problem solving, mathematical applications, and mathematical modeling. These are good things to bear in mind. So now that we have, we are clear on all that, the question is, yeah, but how do I do it? How do we teach in a classroom, right? So I think before we jump into it, I think we need to be able to differentiate between modeling skills and modeling competencies. Like I said before, there is not much point trying to draw a very clear line between, oh, this must be skills, this must be competencies. But at least if we have an idea that, okay, when we are talking about skills, a certain skill set that may be useful for mathematical modeling, then we focus on it. Then if we're talking about things like getting students to make assumptions, list variables, and so on, these are not really, sometimes may not relate directly to the mathematical skills, right? So let us just, for the sake of not, being able to identify them, call these things competencies. So at least we are quite clear that skills refers to really mathematical skills, IT skills, and all those things. Competencies really, has got to do with the modeling process itself. So if we are agreeable on that, then we can move on. The reason why we want to do that is that then we can define a certain hierarchy of learning experience. So my proposal is that let's have a level 1, level 2, and level 3. In level 1, we focus on learning really basic, simple skills. This can be mathematical skills, it can be IT skills, but it has got to be a skill. All right? And in level 2, let's focus on developing competencies. So in developing competencies, by that we mean, for example, the ability to look at a problem and then say, hey, if I want to abstract, I need to make some assumptions. Now, those assumptions that you make and so may not depend on mathematical knowledge, right? It may be just general knowledge, right? Or if I want to be able to look at a situation, what are the variables involved, what are the factors? So maybe these are quite good competencies for us to develop in our students. And finally, at the highest level, level 3, then we put everything together and say that will be a level where we expect the students to undertake a modeling task. Okay? Now, then given this, we are able then to probably think about how we can have a framework that we can be guided in having this differentiated learning experience. Because differentiated to level 1, level 2, level 3 in mathematical modeling. Otherwise, what happens is that very often, this is what I have seen, and also my experience with many teachers is that, oh, I see this real world problem. And okay, this is a very interesting problem. I have no idea what are the outcomes, how I'm going to solve it, and what the model will look like. Let me try it on my students and just plonk, give it to them. That could be one way of, that is what can happen. And at the other extreme, I have also seen teachers who will say that, okay, this is a problem, and do everything very nicely, and what is given to students is just a set of handouts, worksheet, and the students just need to fill in the blanks. And in the end, what happens is that it was the teacher who has been doing the modeling and not the student. So either way is not good, right? Something too open or something too kind of guided may not be help us achieve the objective. So my proposal is that we have this framework. This framework is actually quite simple. It consists of 5 questions: which, what, where, how, and why. When we talk about which, the first question, okay? In other words, this framework is just a guide for you to be able to translate your idea into a modeling activity or modeling lesson. Okay, so the first question we ask ourselves, which? So we need to decide if we want to carry out a modeling lesson or modeling experience, which level are we talking about? So which level of learning experience? It can be level 1, level 2, or level 3. So at level 1, we focus on just basic skills. Okay, like I suggest again that we focus on the skills at level 1 because that is a very basic. If you don't have certain skills, actually it's very difficult to do anything, right? So these skills can be mathematics skills, it can be IT skills, and normally the duration, we wouldn't expect it to be very long, you know, in order to teach students these skills. So it can be 1 period, 1 hour, the kind of thing in your normal lesson, where you teach the skill, but it's in the context of some kind of a real life problem. Okay, so the duration will be fairly short for a lesson like this, level 1. For level 2, we focus on developing the basic modeling competencies now. Okay. And normally that may take a little bit longer because students may not be used to that kind of that way of thinking. Okay, so I would say that maybe 2 lessons, maybe even a couple of days, one day, 2 days, kind of maybe a few hours over two days or something like that for the duration of this lesson. And at level 3 is what we normally would say a modeling task, a full-blown kind of project and things like that, where we expect students to be able to put everything together to solve a problem given to them. Okay, then the next question, what we refer to what modeling skills or competencies. Having decided that, okay, we are going to pitch at a certain level, then I think the next question to ask is that actually what is the problem? So it's important for the teacher to be able to state the problem so that we scope it nicely for the student. So they need some kind of parameter, you know, to work with within certain parameters and within certain constraints and so on. We scope it. Now, sometimes you may not want to do that because you want students to scope it themselves. That's also fine. But they must have already achieved that ability, you know, to be able to make some assumptions and things like that. It will be useful if you are also able to list the kind of competencies that you expect in your lesson, okay, in order to solve the problem. Subtasks. By that I mean if you say, for instance, you need to teach a certain skill. If in order to achieve that, maybe before that your student need to know something else. Okay, so that helps you. If you have all this in mind, it helps you scaffold. And for instance, I used to work with a particular teacher. He wanted his students to solve a problem of designing a car park for the school. Okay, and it actually didn't go very well because his students were not very good with trigonometry. So maybe if he had gone through this and then realized that actually before the students can tackle this problem, you know, you need to at least know more about trigo. It turns out that he carried out his modeling task or lesson just 1 or 2 days after the students were introduced to sine and cosine and tangent. So it was too quick. The students were not used to dealing with trigo functions. So it did not work very well. So, you know, having an idea of what needs to be done can help you plan a more successful lesson. So that is what, okay? Now, this is also a very important point. Where is the mathematics? Sometimes we all get caught, you know, we say this is a very interesting problem and so on, and then you say this is a modeling, mathematical modeling lesson, and then you give it to the students, and the students will do all sorts of things and present and so on, very nice, but no mathematics involved. And I attended a meeting just a couple of days ago, Tuesday, a few days ago, and this is a meeting at MOE, it's a roundtable discussion on mathematical modeling, and one of the teachers who attended the meeting actually shared that they ran this modeling challenge or competition or something like that. And the problem is how do you fill up, how many golf balls do you need to fill up a room, certain size and so on. So say one of the competing schools, one of the students from this, one of the participating schools did this. They have a box, you know, box. And the box is to represent the room. And then they have a lot of ping pong balls. And ping pong balls represent the golf balls. And they just throw everything in it. And they fill up already, then they start counting. It's a model, yes, it's a model. So of course they can then multiply by scaling and so on, right? And then they will know, right? Okay, fine, but it's a model. But when they use a box like this, just the box and the ping pong balls without doing the scaling, actually it's a model, but it's not a mathematical model. It's a physical model. It may solve the problem. It may help solve the problem. But then we need to be very careful. We need to ask ourselves, where is the mathematics? If you say from then you multiply and do some scaling and so on, yes, that's where the mathematics is. If that is the intention, then fine. Okay? So we need to be very careful to know exactly, where is the mathematics that we are focusing on. And then this is also good for us as teachers who have to follow a certain curriculum to link that kind of mathematics that you use in this particular problem to your curriculum. All right? Better still if you can link it to your own scheme of work, then you know exactly when you can try out that particular activity. So where is the mathematics is a third question. The next one is also something I put in there as a suggestion for this framework, because I have seen also work with teachers before who say, okay, this is a problem, and then they just give it to students, but then they don't know how to solve themselves and have never even tried solving it and so on. So then how do you expect your students to be able to come up with a solution? What solution do you expect? What kind of mathematics do you expect them to use? Right? So, okay, it is true that sometimes there can be more than one possible solution. It's true. Your own solution may not be the best. It's also true. But you must at least have something. Right? At least have a solution or have an approach to solving the problem. And better still, if you have more than one approach, more than one solution, more than one way of approaching the problem, I think that's even better. So ask yourself the question, how do I solve it myself if this was given to me, before you give it to your students? And finally, the last question is a why question. Okay, in this case, suppose you are have a set of outcomes, and if you can ask yourself this question, why is this modeling activity a successful one? Then you can measure against the outcomes, measure what you see in the classroom against the expected outcomes in that sense, to answer your own question whether it's successful and why is it successful. Okay, and if it is not, how do you plan what do you plan to do after that? Is there any way of modifying and so on? So this is also like a reflection kind of a question. So in summary, which, what, where, how, why. This diagram is given to you in the notes already. In practice, maybe it's easier to use a table like this. This is exactly the same thing, but it's written in a tabular form. So I encourage people who work with me on this, using this framework, to sort of have two columns like this, and you have all these questions as guiding questions. Some other researchers have done it differently. They have a whole long checklist, and then you just go through a checklist. But I think checklist may be sometimes a little bit too tedious. Okay, so just 5 sections, and then you just fill in the blanks. Okay, let me give you an example. In this example is accident at a certain MRT station. I'm not sure if you still recall this incident. Yeah, and I think it is because of this incident that now all our open MRT stations will all have barriers, right? So, can't remember when, it was 2011. Yeah, this happened in 2011. Thai teenage student lost both her legs after she was hit by an MRT train. Apparently what happened was that when she was interviewed, she claimed that she fell onto the track and because she had a dizzy spell. Yes, her words, she said that. Okay, what happens is that this happened during that time, and this is a 14-year-old girl. So one of my teachers who attended my in-service course on modeling at that time wanted to use this as a modeling problem for her students, Sec 2 students. So 14-year-old, Sec 2 about there, so she thought that it's a good idea, which I think is good, because the kids will be able to relate to the incident and to the problem, you see. So it's relevant, it's real life, but what sort of problems do you want to make out of this incident, you see? So after discussing with that, initially the problem was something else. I don't want to go into details, but after a bit of discussion, this is what we want to focus on. She said she had a dizzy spell, right? And actually this become quite an important point in court, right? Yeah. So if she said that, then presumably we expect her to take a few dizzy steps, meaning few steps around the time, like a drunken, right? And then is it possible that from wherever she was, she took some steps and then fell onto the track without being noticed? It was 11 a.m. at that time, and most of our train stations, this was at Ang Mo Kio MRT station, most of our train stations are fairly crowded. So the problem is, can we ask this question, how many steps would a dizzy person take on average before he or she falls off the platform? Okay, so of course we need to make some assumptions, we need to simplify the situation a little bit, and the idea here is to use a simulation model. Remember we talked about simulation model, right? So suppose this is the platform, okay, and suppose we really do not know where she was at that time. Let's say she started at somewhere in the midway between the two edges of the platform. So these are our axes. So you see we are putting some mathematics in it already, and we have more assumptions. Let's say the dizzy person can only walk in 4 possible directions, 1, 2, 3, 4, and with all equal probability, no obstacles. Okay, and we can actually construct some kind of simulation. I'm going to show you an example on Excel that. Okay, this is an Excel worksheet that I've constructed using a random number and so on. So in this particular case, it's very simple, just Excel without any programming. I'm just pressing F9 to construct a different, each time a different scenario, okay? And then you can see where's the distance, whether the person has fallen off or not, and so on, and at what point, how many steps later she has fallen off, and this can be done with many students, and then you can average out the entire result. But that's not really the whole point of why I want to describe this example. Okay, so now we all know roughly this is a simulation model. So the reason why I describe this example is to ask you this question. Suppose this is the problem that we want to pose to the students, Sec 2. Sec 2, and exactly what I said just now. That means the expectation is for them to come up with this simulation model, use some simulation tool, like let's say for example Excel with random number generator and so on, and then be able to generate data and then start solving the problem and so on. Okay, based on what we have said just now, would you think this is a level 1, level 2, or a level 3 modeling task? You understand what I mean, right? So we have an idea of what this teacher may be thinking of doing. So is this what you think it would be, level 1, level 2, or level 3? How many of you say this is level 1? Unlikely, right? Level 2? Okay, 1 or 2 or 3. Level 3? I think more people would think that it's level 3, right? It's quite complex. I also think that it's level 3. Right. Okay, now we say, okay, finish. This is a level 3. I cannot do it with my kids. Is that true? Because it's level 3, so my kids cannot handle, my students cannot handle. It's too tough. But that's precisely the whole idea of having this framework. So if you think that this is your idea, this is what you want to do, but this is a bit high level, So if I were to carry out in my class, from my lesson image, I will imagine there will be chaos, right? And probably not very successful. That's why we move one step back. Then if this is the case, if this you say is level 3, what is required? What's the main thing that is required in this level 3 task? Coming out with a simulation, coming out with a simulation model, right? Be able to simulate, right? So, in other words, that particular modeling competency of being able to construct make assumptions and so on for a simulation model has to be taught. So that's our scaffold. So in other words, at level 2, could we do something like, instead of having saying that we want to simulate the whole MRT problem situation, let's say we just take simulation a person. I don't know whether you have come across this, a random walker problem. That means this person can only walk left or right. Right? And if you do that, okay, you either take a step in a positive direction or negative direction. This is where you end up. Suppose you start with 0, you take a positive step 1, you end up at position 1, you take another positive 1, you end up 2, and so on. So in fact, you can run a simple simulation and find out where is the person at the end. And if you average it, where do you think on average, where would the person end up after, let's say, a large number of steps? You know? Where's the likely place, most likely place? You know what I mean? It's a random walk. Starting from 0, you either take one step, or you take one step like that. So the positions are marked on the, say, the integer, positive, negative. You start at 0, right? And then then maybe you toss a coin, a fair coin. Heads, you take one step in the positive direction. Tails, you take one step in the negative direction. Okay? Equal chance, huh? Yeah? So my question is, on the average, in the end, after many steps, where is the most likely place that this person will end up? Do you know? Okay, what is the distribution? What is the distribution of the final position of this person after a large number of steps? Do you know the distribution? Normal. So the most likely position is back where you start. This is for large N. Try it. Okay. So this, as you can see, would this then provide the student with the kind of skill? Because the simulation, right? There's simulation involved. There's random number generator involved, and so on. That will help in the level 3 problem. And you can also link this to your A-level syllabus, right? Normal distribution is there, right? Probability is there, right? And so on. So this, I would say, is like a level 2. But before we can even reach this particular simulation, we need to know something about generating random numbers, about simulating tossing of coin or whatever and things like that, right? So we need a level 1. Okay? So probably a level 1 will be a very simple one. Let's say I roll a pair of fair dice. Okay? And then I can teach students about, I think this one we went through, right? Remember? Right? I did something similar in one of the sessions, session 2, right? On random number generator. And we can, that concept, especially for A-level students, for example, I don't think it's that hard to teach them. Using a random number generator, just generate something, generate the outcomes of a fair dice, the tossing of a fair dice. And then 1 is actually nothing very much. Let's toss 2. And then find the sum, and then, maybe construct some kind of a distribution table. Okay, so the whole idea is that if we have a a systematic way of looking at a problem. All right, and going through the framework deciding first of all which level we want to pitch our activity at, or the lesson at, or the learning experience should be at which level, what kind of skills and competencies we want our students to learn, where is the mathematics, how do we ourselves solve it, and at the end, what do we expect to see in order to answer the question, why is this a successful activity? And the whole framework then can guide us into basically planning and at the same time implementing a lesson, which I think will probably be more successful than you just take something from somewhere, some resource, and then just try it out. Okay? Nothing wrong with trying to get resources from the internet or from books and so on, nothing wrong, but you must then put it into your own context. I think that's important. And before you can do that, it's also good to go through those questions, ask yourself those questions, so that you have a systematic way of deciding making some of the decisions when you're designing and implementing the activity. Of course, I have to say that all these things that I've said is not something that I just dreamed up last night. It took some time before, I can consolidate all these experiences together to share with you. So I don't expect you after today, tomorrow suddenly you are able to plan 10 different kind of lessons for your students. I don't expect that, but it takes time to build. But at least having a kind of framework helps you move a little bit faster in designing. So at this point, any questions from anyone on this framework? Any questions? If not, we can move on to the next part of today's session.